All right. Hey everyone. My name's Adrian. I've been working with Emily on an AA290 this quarter. And the topic of my research is to really look into optimal key point selection for SPN. And I'm here to give a pretty big research update on my progress on that. So first of all, I'll just start off with a bit of motivation on what SPN is, just as a refresher in case any of you don't really know too much about it. It's just a key point detection network that estimates key point locations for pose solvers and navigational filters. And this is useful for, close range proximity operations in space where you have a camera that needs to take pictures of a target spacecraft and estimate the pose. And yet it does this by estimating specific key point locations on that spacecraft, which is then used in these solvers. And the motivation behind my work specifically is that SPN is trained on key points, but these key points are currently manually placed on the spacecraft geometry. Typically, if you were doing this, you would abide by some type of heuristic that would include placing them maybe on corners or appendages for box-shaped satellites, maybe like solar panels or antennas. But these type of heuristics can, break down for non-conventional shapes, such as like cylinders or, rockets or even super complicated satellites that you might have a model of, but you might not be too sure where to put the key points. And so the problem statement for me really is to develop a way to automatically find an optimal key point geometry for pose estimation performance. And I'm going to go a little bit into what it means to be optimal. Part of the definition I'm taking on is that the key point subset should also be robust, because in any case that a point isn't detected, which I would consider a dropout, pose estimation accuracy can degrade because you don't have access to that information anymore. In space, this can be caused by poor viewing conditions such as occlusion or light glares that might oversaturate some part of the camera sensor. And so therefore, to me, an optimal key point set should also be resistant to dropouts with minimal accuracy degradation. And, as some type of example targets where it might be difficult to, use heuristics to manually place key points, it could be rounded shapes like rockets that don't have, intuitive manual point locations based on these heuristics, for example, like the Blue Origin New Shepard, or it could be complex targets that might also have non-obvious key point locations, such as the Mako spacecraft, which is the model on the right. And so the prior work regarding this primarily gets split up into two camps. There have been some recent ML approaches that try to learn key point locations. Overall, these works demonstrate that placement and distribution do matter, but their approaches vary wildly or significantly. Some of them introduce different network architectures that optimize key point learnability. In the case of one work that I saw that optimizes key points for a detection network that uses voting instead of just the heat map method that the SPN uses, or instance adaptation, another network that I saw that tries to learn different instances and categories of objects and then placing key points on them. Again, these are a bit different architecture than what SPN currently has. And another method I saw attempts to learn optimal down selections online based on certain metrics on uncertainty and spatial distribution. So the niche I'm kind of leaning into here is more like the offline side and the pre-selection for the detection-based networks such as SPN. It seems to be a bit of a gap that I've noticed. Another camp is the analytical approaches, which utilize geometric information theory to reason about pose estimation accuracy. Some works use disk covering methods to enforce spatial distribution. This happens when you take key points and kind of draw a disk around them, and then all the other key points that you select have to be outside of this disk, so it makes sure that they're spaced apart relatively well. Others go a bit further and quantify measurement sensitivity using linearized models. And other more recent works perform covariance recursion using feature placement and trajectory as design variables to kind of get sensitivity signals from, for example, differentiating Kalman filter dynamics to get an idea of where would be more optimal positions for the key points. The approach I'm proposing is to instead formulate this selection as a robust optimization design problem, or kind of like an experimental design problem that instead takes advantage of efficient log determinant scoring as a surrogate for performance. I'll get a bit more into that later. And also samples these scores across many different quote unquote scenarios for coverage and generalization. Or it can also sample from scenarios that you select to follow a specific mission guideline. I'll go a bit more into that as well. The point of this is to utilize submodular optimization with pretty strong optimality bounds as established in that branch of literature, and also be customizable to optimize for worst case or some type of tail expectation. And I've included a diagram of what the pipeline looks like here, and I'll go a bit more into it in the following slide. Or the following slides. The advantages of this approach is that dropouts are included in the scenario objective functions, which means you can explicitly model and target robustness. Mission scenarios can be modeled explicitly to the solver. So if you have ideas of what exactly, or like the general trajectory or the viewing angles will look like on the mission, you can input that into the solver. You could also, again, make it generalizable by having a diverse set of scenarios and with high sampling. And your performance needs can be customized based on the hyperparameters input to the optimization functions. The current assumptions, which I will mention, are more like limitations on what's being currently modeled fidelity-wise, are the measurement noise is assumed to be uniform. Dropout probability is currently assumed to be uniform. The big one is perfect 2D, 3D correspondence, although I will mention that as part of its architecture, SPN is designed to try and find heat points for each individual key point. So the correspondence should come out of SPN naturally if it's working well. And then observability and saliency is also unmodeled. This is currently based on geometric information. Although, like I said, with more fidelity and more modeling, these assumptions could be tackled with more detail in the future. This is just currently where it sits right now. So to get a little bit into what's going on behind the scenes for my implementation, I'll talk a little bit about some of the terms that I'm using. For the Jacobian log depth metric, that is kind of like the objective that I'm using for my functions. The basis for this is that key point measurements are just 2D projections on a camera plane, and with proper correspondence, pose solvers can determine a 6D pose from these 2D measurements. The sensitivity signals can come from a linearized model of the key points with respect to perturbations in pose, whether it be translation or orientation, and a higher sensitivity means more constrained pose solutions. So if you take these measurements, these projections on a 2D camera plane, and then take linearizations, Jacobians, these will give you, and take the log determinant scoring in an information metric style approach, this can give you a sensitivity signals to how informative a certain set of key points can be. And so I'm using this as a surrogate because these can be efficiently computed and can represent how well a pose solver can accurately determine the true pose. And I'll get more a bit into the validation of this later. For the state-of-the-art algorithms that I'm implementing, the first one is called Saturate, which is based on a paper in 2008. It does submodular robust optimization that attempts to maximize the worst case objective function, subject to the subset being within the cardinal size that you set. To maintain submodularity, the problem is reformulated into a kind of like a threshold variable C, where it does a binary search on C to find the highest C that all objective functions can satisfy. And this enables greedy accumulation of key points because it's submodular, and they show in the paper that there are no better optimality guarantees that efficiently exist because this is an NP-hard problem. The other optimizer that I've implemented is called Sequential Greedy Algorithm Conditional Value at Risk. This is based on a 2018 paper, which does submodular robust optimization that attempts to maximize the expectation of the lower alpha tail of objective functions. And so they use an auxiliary function that is dependent on tau, which is a variable that gets explored, as well as S, which is your subset. Subsets are greedily built and chosen so that this auxiliary function is maximized for each tau in a search grid, and the solution is the best combination of the objective function based on whatever subset and tau that maximizes the function, since the auxiliary function is concave in tau given S. So I know it's a bit complicated, but really all this is just trying to find a subset that keeps the expectation of whatever tail. You can set alpha to be whatever you want to be. You can be 10%, 20%. The tail as the expectation to be as high as possible. And again, this is an NP-hard problem, so this is an approximation, but since this is submodular, there are some pretty good optimality bounds with greedy algorithms. So the overall implementation of my pipeline is basically to load the model that you have available. This could be a CAD model or STL file, PLA file, PLY file, and a scenario bank. And what I mean by a scenario bank is that a scenario is any viewing condition and any dropout condition that you may have. So viewing condition is whatever quaternion or translation vector that you have that dictates the orientation of the target and how far you are from the target. And then dropouts are whichever key points are available to be used or whichever key points are unavailable to be used. Step 2 is to populate the model with candidate key points. Here I have a picture of the Mako spacecraft with 70 candidate key points. This can be done potentially automatically if I have implemented a way that uses an algorithm called intrinsic shape signatures, but I've also introduced the way that you can just click on the model and you can place a key point there. So it's not too bad and it's pretty fast. Step 3 is to down select using one of the submodular optimization algorithms that I talked about. And then from there, you would have your optimized subset that you would feed into SPN to train on. And when this picture here I have is a down selected from the 70 key points for the Mako spacecraft using the CVAR algorithm, and you down select from 70 to 16. And how much you want to target, you can also select that, how many, what the size is of your optimized subset. And this would be based on constraints on, how many key points SBN can handle, the network size there. So this would kind of be more of like a hyperparameter that gets determined by other constraints. And so now I'm going to go into a few validation studies that I've done. This is basically comparing the log determinant scoring metric that I've implemented versus what you would expect from performance. How this works is that I simulate the PNP error by taking those 2D image plane projections and adding some noise. I believe in this case it was just 1 pixel sigma, and then running those noisy image measurements through a PNP solver and seeing how accurate it is compared to the ground truth. And you can see here as you rotate this. This is just Tango, the 11 key points of Tango. You can see that in general, higher scores result in lower error. I have 3 scores plotted out on there. It's the ones to pay attention to. The ones to pay attention to are HX and HC. Those two kind of quantify the measurement sensitivity, and also HC quantifies sensitivity that includes potential map bias, which is another thing else. I can get into it if there's time, but those are just some of the scoring metrics that are used. And yeah, this basically shows that higher scores typically correspond to lower errors, and you can see that through the graphs in the middle.
Adrian, can you close the bar at the top?
Oh,
okay. Yeah.
Sorry.
Thanks.
The next validation study I did was to basically look into optimizing the Mako model. So the scenarios that I fed into the optimizer were 10,000 well-distributed scenarios, all from speed. These would be the quaternions, the orientation, and the translations. And for those n equals 70 candidate key points, I made it so that each has a 25% uniform dropout probability per scenario to kind of give a broad range of possibilities for what the optimizer will see. And again, the target down selection size was k equals 16. For kind of like a control subset comparison, I also looked into the performance of a manual selection where you taking a naive heuristic of just picking only the corners. And this would also be for 16 key points. So what we see here after the optimization is done, this is a comparison between the CVAR selection and the manual corner selection. We can see here that, and again, the simulation for the ePNP for performance is the same. We can see here that the new selection done by the optimizer is consistently better than the manual selection. You can see in the second, well, I can't really point to it, but the second graph on the right from the top. The manual corners EPMP solution generally has more error overall, and you can see how the score is lower overall. So again, this kind of reinforces the idea that score is a pretty good measurement for how accurate the pose is going to be. Although, you can tell that the points that the optimizer selects are still mostly the same. So the interpretation here is that it is going for the points that are very well spatially distributed. And that does happen for Mako to be a lot of the corners because they are quite far apart. But there are a few differences. I know it's pretty hard to tell here, but maybe if I go back to this slide, you can see it does include 2 points on those nubs at the top. And then on the bottom, it's a little bit hidden. There's another point on the nub on the bottom that kind of breaks the coplanarity of all those corners, and that helps it slightly more when it comes to your average performance and your tail performance. And we'll see that in some data here. So this animation was done without any dropouts, but to evaluate these subsets over the any potential dropout scenario, I made a validation set of scenarios, which are 15,000 unseen scenarios, also from speed. This time slightly out of distribution as well, because I increased the dropout probability to 30%. So this is a little bit harder. And we see in the injected noise, I made it 2-pixel covariance with 0 mean. And we see here that even in this harder distribution, I know there are a lot of metrics to go by, so I'll kind of go through them a little bit slowly. For the scores, CVER does better, and I know they all look pretty compressed near 1, but that's because they are normalized against a very low floor. So to kind of get a more intuitive sense of what this means, I included the statistics when I ran the PNP simulations. We see that the mean translation error, which is ET, it gets improved by both the optimizer algorithms. The mean orientation error, which is EQ, gets significantly improved, cut down by half. And that translates to a significantly better pose error, which is the metric defined in the SBNV3 paper. It's just it's the normalized translation error plus the orientation error. The standard deviation is best for the saturate selection, and we see that there are quite some bad instances in the manual corners only subset. The standard deviation is like 4.5 degrees. So there are some really bad instances where dropouts can really degrade the pose solution there, but it doesn't affect the optimized subsets as badly. And if we look at some more distribution statistics, we see that the 90th percentile, which is like the 90th percentile worst cases, which is on the opposite tail, it's the 90th percentile because it's higher, and higher is worse for pose error. We see that the optimizer algorithms improve the 90th percentile in all 3 categories. CVR does the best because it targets the tail rather than just the worst case. But there are, out of all the scenarios there are, if we look at the exact worst cases, Saturate does a pretty good job in making sure that the worst case scenarios aren't completely, degenerate. And to take a look at those worst case scenarios, we can see that in the manual case, it is as you would expect. It is the worst case scenario happens when the only surviving points are those coplanar points on the solar panels and the bottom side. And then for the CVR, it's kind of the similar case where you have the only surviving key points being on that flat base on the bottom. I know it's a bit hard to tell from these pictures, but you can kind of get an idea. As it turns out, again, the most well spatially distributed points for Mako also happen to be fairly coplanar. And so this is kind of the balance that needs to be struck. I would imagine if you change the scenarios to be more difficult, then it might try to find more safer sets of key points that don't necessarily have as high of a mean. But again, this is all something that can be dependent on the scenarios that you feed it. For example, how Saturate handles these cases, we see here that Saturate actually does have 1 point that's kind of in the middle of the spacecraft that breaks the coplanarity. And if it's available in that situation, then it significantly drops the error as you would expect. And the same thing goes for the case on the right. So the conclusions that can be drawn from these studies is that key point preselection can impact the quality of pose estimation significantly. These simulations suggest that optimal preselection can improve the estimation accuracy of detection models such as SPN, and that offline optimal selection can be formulated as a robust optimization design problem The use of these submodular surrogate functions enable access to powerful and near optimal polynomial time algorithms for the NP-hard problem. It's useful for non-intuitive spacecraft geometries, and mission scenarios can be explicitly seen in the optimization set, and generalization can occur through high sampling and broadly distributed scenarios. In terms of the next steps, I do want to continue performing additional studies to show stronger use cases. Current studies, as you can probably tell through the results, suggest that the approach does make some improvements, but not like that much compared to what you would have off of a naive heuristic. An additional study can involve maybe a scenario bank of a mission-defined approach trajectory with closure distances that push some key points outside of the camera view. I had a conversation about this with somebody this morning, so this is fresh off the press. Um, After that, I would be interested in doing validation studies with real data, perhaps training SPN on these optimized subsets, and then gathering some software in the loop or hardware in the loop performance data to really see how this holds up outside of simulation. And then from there on, I would also be looking into modeling additional fidelity through observability and dropouts, investigating means of modeling this, visual saliency of these points, covariance and dropout probability of key points before optimization. And this is kind of a bit out there right now, but perhaps with enough fidelity, perhaps a machine learning approach can also be considered. And yeah, that's what I have.